Hey everyone, this is our Senior Design 2 project. It's the Duke Transmission Outage Scheduling Optimization Project Overview. So first we'll start with the team. From left to right, as you can see in the pictures, it's Matthew Hughes, Daniel Ponsetti, Caleb Shelton, Nick Burns, and Ryan Dehay, and we're all senior electrical engineers here at Clemson, graduating in May.
Our motivation for our project was very simple. Our team all shared a strong interest in the power industry. It really helped that three of our members have had prior experience working in the power industry, specifically on the distribution and a little bit on the transmission side. And then from that, we all wanted to gain practical experience on the transmission side of the industry. And lastly, with our picking our senior design project, we wanted to be able to communicate with a working professional, and that's why we chose an industry-sponsored project.
The problem definition of our project. So power grids must continuously evolve to meet increasing load demands and technological advancements while ensuring safety, efficiency, and cost effectiveness. So our solution was to develop an optimization program that simulates a power system with required outages and optimizes scheduling for reliability, safety, and efficiency.
For the description and discussion of our design, we had a couple things. First was the purpose. We were supposed to optimize the transmission out of scheduling using the reliability centered maintenance, the RCM method. And we also used the N1 contingency analysis to ensure the power system was reliable. With the RCM integration, it prioritizes assets by importance and assesses the risk by deferring maintenance using reliability metrics. For the N1 contingency analysis, it simulates single element failures. This ensures the system's stability, which means no overloading, and it uses the power flow analysis to do this. For the output, it provides outage schedules, reliability metrics, and contingency analysis results for ensure to secure system operation. You'll see this in a little bit.
So our performance analysis of our project. So we originally started with a MATLAB code from a previous semester's work, which it took about 2 to 3 hours. We converted it to Python and it took us about 25 minutes to execute. So that's an overall speed of around 6%. It generates a prioritized list of branches that need maintenance on the grid, schedules schedules these outages to minimize system impact and grid strain, and then considers the worst case scenarios during peak load conditions, and then produces an optimized outage plan that respects system constraints so we don't have any extra outages. And then project strengths. The GUI we have is very intuitive and gives output data in multiple forms that are visually easy to follow and comprehend. And then our software is also very efficient and calculates accurate values for transmission outages. As stated before, it's about 6 times faster than the original MATLAB code. And then our software can correctly assess transmission planning. It does this by dynamically adjusting based on parameters to reach our best possible outcome. Our code also performs RCM as mentioned earlier. This increases the reliability of the grid by focusing on reliability and decrease negative outcomes. Um, there is some challenges with RCM in dynamic grid environments because it might become misaligned with real-time operational needs because it cannot capture evolving grid conditions.
Our project also has some weaknesses. Our code is limited by the lack of simulation iterations, the Monte Carlo simulations. This really means that it does not have randomness built into the code. Also, another weakness is the limited data set was provided. This restricts our ability to be thorough and test the code across a broader range of scenarios. And then lastly, with the project being done in 2 separate semesters, there's 2 separate groups looking at this. And this means that there is essentially no continuity. We didn't have to start from scratch whenever we started this project, and this made it a little bit harder for our group, but ultimately I believe that it was the best decision that we've made because working with what they made was not efficient.
And now we'll go into a live demonstration.
This is the practical portion of our demo. I will go over the different aspects of our code, going into the high level of each of the major functions. Then I will bring up the results that are offered at each major section, and then I will go over the GUI and give a demonstration of what it can do. So we were first given this as our initial case study. It has all the bus indexes and a lot of the other data. All the important data that we need is highlighted at the top in yellow. We have the load, the generation, and the other branch. And then this was us doing extra testing for the code. So in our main simulation file, it handles the N-1 contingencies. It does the RCM optimization techniques, and it imports and exports the bulk of our data. So here, this function runs our N-1 contingency and finds any failed branches. It also loads our initial case data. Then this portion of code is our RCM. Below are all of these are our defaults that in case the code does not get correctly loaded, it will run through a pre-built simulation. That way we can test if any of the other portions of our code is working. Then we have some functions that reads and writes all of our results to Excel and formats all the data in a relatively nice way. We store some data in the .txts, like right here. So we have a log of the simulation, which goes through all the data that gets inputted. And then we also have another .txt, which has the bare minimum of the data that we need. And here we have initial multipliers to play with all the conditions and values and all the different extremes. The RCM requires some of this data. And it's also pretty important to see how the results change by changing some of these multipliers. And here we load in all our base data, and this is where all the functions get called and the actual simulation gets run. So with that, the simulations run and it gives us all these different cases in our Excel folder down here. And then this was the base N-1 contingency, and then this is our case 2, which was our best case. And then these are all the other cases. This is pretty much the exact same code, except it can run all these simulations concurrently. So there's no manual input, because before you would have to manually input. We are working on case 1, we're now working on case 2, etc. And this portion does all of that automatically. Here, this creates a transmission map for the GUI. Most of it is pretty in-depth, but it essentially takes all the initial data from in here, which is the bus index, the name of the node, and which ones have a generation on it, and also the from and to for each section. And with all that data, it creates a transmission map. And then this basically creates that from and to bus into a readable format. So this is our GUI code. It handles pretty much all the aspects of all the other code, and you can control everything from here. It's the main brain of our operation. This loads in the transmission graph data, so and then also adds an overlay so you can see where the outages are. We'll highlight them in red. And then going further, this parses the data so we can read it. Here we initialize our GUI and create different frames for organization. And then here we plot our findings also in a dual bar graph so you can compare different data points. And the rest of the code just focuses on making sure the GUI looks relatively clean. And here you will bring up the GUI. So this is our GUI. There's a lot of information going on here. So this is the dual bar graph. You can see the real power and the reactive power. Also shows the branches and where it is here. You can also start a simulation and select which case you want to work on. We have 20 cases here. And then this is our transmission interactive map. So you can hover on each of the nodes. The blue nodes are buses, the green is our generation. You can see the name of each node. And then if there's an outage, highlight in the red, you can hover over it and you can see the direction. So it's going from olive to Beltline, and the real power and the reactive power lost. And then up here, it shows the total real and reactive power loss. You can play around there. You can also switch and see the other cases. So this would be our case 10. It's a bit more of power loss. And you can see the outage map changed along with the bar graph. And then down here, you can also see all the different, the raw data, essentially. And then you can scroll around. You can also start the program here. It does take a while. You can kind of see it running in the background. But to actually go through the analysis, it does take, takes about 10-ish minutes. And that is our demo.